Okay, so good evening. So the topic as I have for the last few classes, the way I mean it will follow on the same in the same way. Like we'll take 10 questions which are taken from last year's assignment, and and I'll be solving them. So these questions are pretty simple. So if you have any doubts in between, or after going through the questions, you can ask me doubts. And even while solving the question, if you face if you have any confusion, you can ask me. I will try my best to clear them. So let's jump in. Yeah, okay. This is quite fine. Okay, so the topic for this week was linear classification, logistic regression, linear classification. Uh, so So the first question is regarding that. So I hope the screen is visible. I'm zooming in a bit more so that it's visible to everybody. I guess this is fine. So for linear classification, we use a linear function to separate the classes, a linear function to model the data, and a linear loss or a nonlinear function to fit the data. So can one of you guess which is the answer? Yeah, I'm seeing a message that somebody has said about A. Yeah, it's correct. So for linear classification, we want a linear function to separate the classes. Basically, the decision boundary that you are learning in order to separate the classes will be linear. The second question, I'm not sure whether this is correct or not, the answer for this, because okay, so logit transformation. So logit transformation for probability of x equal to 1 for given data is so the data is given as 0 1 1 0 1 0 1, and you have to find out the logit for probability of x equal to 1. Now probability of x equal to 1, if you see here that there are 4 cases out of 7 cases in which the probability is turning out to be 1. Therefore this is 4 by 7, and probability of x equal to 0 is therefore 3 by 7. So the answer for this has been marked out to be 4 by 3. So actually there is a log function in here, but the log is not appearing in the answers. So I don't know whether this was an incorrect solution or some incorrect question or not, but I guess there would be a log in front of all of these. So if you want the logit, okay, let's write it in that way only. So logit for probability of x equal to 1 is defined in this way. And here if you see, this is 4 by 7 by 3 by 7, and therefore the answer should be log of 4 by 3. Log is not there, and the corresponding answer has been marked to be 4 by 3 in the last assignment, but ideally this should be log of 4 by 3. Okay. Then the third question is quite simple, like output of the binary class logistic regression lies in this range. So you will know that, it finally outputs a probability. So the output of a binary class logistic regression would be a number between 0 and 1. And therefore this is the correct answer. Okay, so the three questions. So the fourth question involves it's all easy, but it involves a bit of a math. So log of 1 minus px by 1 plus px is given to be a value, and you have to solve for px. So basically this is just solving this equation. So let's say I have 1 minus px by 1 plus px equal to e to the power of beta 0 plus beta x. And from here you can write 1 minus px equal to e to the power of beta 0 plus beta x into 1 plus p of x. If you take p of x common, and if you now accumulate terms corresponding to p of x, then it would be something like P of x, this, okay, P of x, this e to the power of beta plus beta 0 plus beta x will come, and apart from that there will be a plus 1. So that is it, and on the other side, be common. And on the other side, it will be 1 minus e to the power of beta 0 plus beta x, and therefore px equal to 1 minus e to the power of beta 0 plus beta x by 1 plus e to the power of beta 0 plus beta x. And that is this particular option. Option D is the correct one. I hope this is clear. Then the logistic regression is robust to outliers, and the question is why. So logistic regression, if you know that, I mean, if you have gone through the lecture, you will see that what it does is finally it takes a softmax function. So it will do it will learn something, and finally at the end of the day it will do something like e to the power x by 1 plus e to the power x, where x is your whatever x is your linear function, let's say. Okay, uh, let me put this to be z, then otherwise it might be confusing. So beta 0 plus beta z is something that you learn linearly, and then you take a softmax function of that. And so the softmax of something looks like, um, it looks like this. So you see that it looks like this. So even if x goes very high, suppose x is growing very high on the right side of the x-axis, and x is going very low on the left-hand side of the x-axis, but because of the saturation property of softmax, it will not be affected by all these. It will not be affected by all these outliers. So x growing very high is an indication of an outlier maybe, and x going very negatives also might be an indication of an outlier. But because of the way softmax is squashing everything between 0 and 1, that it will not be affected by the outliers that much as compared to other learning algorithms, and therefore the squashing of the output values between 0 and 1 dampens the effect of the outliers. So the other thing that was taught extensively in this week was LDA, which stands for linear discriminant analysis. So, so the first question is, what is the aim of LDA? So, if you go through the lecture, you will see that what LDA tries to do is it will try to um, yeah, it will try to reduce the intra-class variability, which means that, let's say you have two classes in your data. You have two classes like this. This is one class, let's say, and you have another class which is something like this. So you will what you will try to do is you will try to project this on some lower dimensional plane. So suppose you try to project this here. So what you try to do is you try to minimize the intra-class variability and maximize the distance between the mean of the classes. So why do you want to do that? You want to do that because you want all of these to be very close together and all of this to be very close together, and that means that you are trying to reduce the intra-class variability, that all your points corresponding to one single class should be very close to one another. At the same time, you want to separate them out in the lower dimensional space, and therefore you want to maximize the distance between the mean of the two classes. So, so these are the two options which are correct. That you would try to minimize the intra-class variability. You will try to get all the points belonging to one particular class together. At the same time, you would want to maximize the distance between the mean of the two classes or mean of the classes. So that is the aim of LDA. Then we have two classes in our data set with mean 0 and 1 and variance of 2 and 3. So if you see that, so mean of 0 and 1 means, so if you plot this, so this is the mean of one class. 0. Okay, and this is the mean of the other class, which is 1, and you have a variance of 2 and 3. So like this is, if you consider this, what would high interclass variability mean? Okay, high interclass, we are not talking about interclass variability, we are talking about intra-class variability. Okay, so intra-class, okay, so let me give you a graphical example that would be better, I guess. So this, so suppose your points are distributed in such a way that it looks like this. So all this big ellipse that you are seeing, that I have drawn, is an example of is an example of how your class distribution might look like. Similarly, your class distribution may also look like this. So suppose you have the same number of points in the black circle, in the black ellipse, as well as in the red ellipse, but the intra-class variability is much less in the black case than in the red case. Okay, is it clear now? Somebody has asked this question. I saw in the chat, I guess. Yeah, so Vishal, I think. So is it clear? Yeah, okay. Thank you. So now where was I? Yeah, okay. So I was trying to solve this. Okay, yeah. So suppose your two classes, and let's consider your class distribution to be Gaussian. So if your class distribution is Gaussian, then of course you can see that the mean being 0 and a variance of 2 means that it will be like this. So it will be like this, and a mean of 1 and a variance of 3 means it will be like this. It will have a slightly larger variance. So of course you can see that the data points here in this particular case, they are not linearly separable, and LDA can't separate out points which are not linearly separable, and therefore LDA will definitely not be able to classify them perfectly. Okay, so that would be the correct option. The next option is a bit tricky in the sense that now we have the mean of 0 and 5. So mean is, let's say, 0 here and 5 is here, and variance is 1. So this means that variance is coming out to be 1 and variance is coming out to be 2 in this case. Now so you might be tempted to answer that, yeah, LDA will definitely be able to classify them perfectly, because in the last case you had seen that LDA will definitely not be able to classify them. But you see, these are all, yeah, these are all statistical things. So that means that it is not like variance 1 and 2 means data points will only come from this particular from this particular area that I have drawn. They might come from much farther away from the variance. So it depends on how the points are actually distributed. So therefore, unless you see the points just by looking at the mean and variance, you might claim that LDA will definitely not be able to classify them perfectly. But um, in order to claim that LDA will be able to classify them is difficult. You need to look at the points. Only then you will be able to understand whether LDA will be able to separate them. Therefore, the option will be LDA may be able to classify them perfectly. That is one. The next thing is for the two classes plus and minus shown below. So these are the two classes. If you can see, these are the two classes that I am circling. These are the two classes plus and minus. While performing LDA on it, which line is the most appropriate for projecting the data points? Now, if you know that what happens in LDA is the line on which you will project these points is basically should be parallel to the line which are joining the two means. So the mean of the very sorry. Yeah. So the mean of this particular cluster would be here, and the mean of this particular clusters will be somewhere here, and the line joining them will be like this. Yeah, and the line joining them will be like this. And you see that the blue line is the one which is most parallel to this particular line, and therefore the option would be blue. And finally, this is another way to interpret LDA, but not necessary, because LDA can be performed even when the data doesn't come from the Gaussian distribution. Yeah, so LDA assumes that the class data is distributed in a Gaussian sense. But this is not, LDA can be performed even when the data is not Gaussian. I mean, you don't want, there is one interpretation of LDA where you can go ahead without looking at the Gaussian interpretation at all. So that is another way to interpret LDA. In the classical way in which LDA was defined or found out, it was mainly found out because of this Gaussian distribution of the data. Yeah, so I solved through the questions. They were pretty simple, so it did not take much time. So now if you have any questions, you can ask. Okay, please show 3 and 5. 3 and 5. Okay, for 3, you see what happens is, um, yeah, so as I said, so for logistic regression, what would you do? You would learn something. Let's say you have learned Z. Z is beta 0 plus beta x, let's say. Or, yeah, okay, let's say you have learned beta 0 plus beta x. So beta 0 plus beta x is some linear function that you have learned. And then you take a softmax of this, right? So the softmax of this would be beta 0 plus beta x by 1 plus e to the power beta 0 plus beta x. Okay, so hello. Yeah, so if you see this, this always lies between 0 and 1, and therefore the answer of this would be 0 and 1. Clear? Hello. Yeah, okay. The other thing that you said was 5. Yeah, and it is precisely of the same reason. So what happens is, so this function, if you plot it, it would look something like this. So this is 0. So let's say this function is looking like this. Okay. This function will generally look like this. It is also known as a softmax function. So this will be 0.5 at 0. And so if this, that also depends on beta 0, but let's say so right now, let's say that you have set beta 0 to be 0, and therefore at 0 this would turn out to be 0.5. Okay, so when you have zero point 0.5, so you see, how can I say this? Okay, okay, so one thing that you have to understand, okay, let's show this in a proper way. See, one thing which you have to understand is, mm, how can I show this? Okay, so the loss function for logistic regression is something like this. Okay, y log y hat plus 1 minus y log 1 minus y hat. Okay, this is the way logistic regression, the loss function of this comes out to be. And so you see that what happens is your loss function. So, and this y hat is precisely the value that comes out after doing this. Okay, so y hat comes from here. So y hat is this particular function. So now you see that, and this is a, so this can't be solved normally. Like for linear regression, you had done something like x transpose x inverse x transpose y. This was a solution for linear regression. This particular problem can't be solved in this way. There is no direct solution. You can't just solve this, take a derivative and set it to be 0, and then find and give the output of that. So you can't find this out. This is very difficult to solve. And therefore what happens is this is solved in iterative fashion. So there is something called gradient descent. So what you need to do is you need to find out the you need to find out the gradient of the loss with respect to the parameters. So the parameters might be beta 0 plus, sorry, the parameters would be beta. Okay. So you need to find out this gradient. And once you find out this gradient, you will have to reduce the loss function in accordance to the gradient. In the sense that you would take steps in the direction of negative gradient, right? So once you do that, what happens is your loss goes on decreasing. In every step, your loss goes on decreasing. And as your loss goes on decreasing, that means that you are performing well, better and better on your training data. Now, you see here what happens is, in this case, just look at the loss function, how it behaves. You see that, let's say x is 10 here. Okay. This is just a, I mean, this is just a value. The x is 10 here. And let's say x is 10 to the power 5 here. You will notice that if you have this particular function, e to the power x by e to the power x plus 1, the value of this particular function of e to the power of for x equal to 10 and x equal to 10 to the power 5 will be very close to each other. So even if, so suppose all of your values were lying in this particular zone, only one value was lying here. And this is x equal to 10 to the power 5. Rest all values were, let's say, x equal to 100. So if less than x equal to 100, but the value that you will get for y, even for x equal to 100 and x equal to 10 to the power 5 will not vary by that much. And if your y hat doesn't vary that much, then your L will also not vary, right? And if your L does not vary, then you won't learn any differently than you would learn for 100 and 10 to the power 5. And therefore, it will be robust to outliers. Did I make myself clear or did I confuse you more? Hello? Clear. Thank you. Okay. So 3 and 5 you had said. Okay. Yeah. Any more questions? Answer is Gaussian. Yeah. Yeah. It doesn't assume anything. So I think two interpretations of LDA were taught. And the two interpretations are are exactly similar in some sense. But the second interpretation, I like it more because that doesn't take that Gaussian distribution into account. And because generally in LDA, you won't apply LDA only when it is Gaussian. You will apply LDA even when you don't know the distribution. So, so LDA is general in that sense, right? Answer is C. Answer is C, but LDA does not. So this is like, see, this has stuck on for historical reasons maybe. So LDA was first initialized for when we had this Gaussian assumption, but afterwards a different way to treat or to understand LDA was found out, which doesn't take that Gaussian assumption. But since LDA initially had that Gaussian assumption in mind, therefore it is this question. The answer of this would be Gaussian. Okay, so any more questions? Like, was this particular point clear? Like, why this would be parallel to? I mean, this is just from LDA, from the second definition of the second interpretation of LDA. So this comes from that. Basically, it would be parallel to the different. It will be parallel to the line joining the two means of the two classes. Okay, so this comes from there. So nobody is having any more questions. Let's see, is there anything in chat? Okay, chat, please show 3 and 5. I have already shown 3 and 5. This is a old chat, is it? Shahid, you have asked to show 3 and 5. Ah, okay, okay, fine. Okay, if there are no more questions, then should I close the call? I mean, this is a very short class then. Okay, thank you, everyone. Thank you. Yeah, the recording for this class is available on YouTube, and I think I don't know whether NPTEL provides you with those links because everything is there on my YouTube channel. I don't know whether NPTEL provides you those. I mean, I give, yeah, I'll give that. Just give me a minute. Yeah, yeah, I have pasted it in the message box. You can directly go here and you will find the videos of the last 2 weeks also. So, yeah. Yeah, since I'll wait for some time for others, maybe if somebody joins. So, you guys are free to leave. Thank you. Okay, somebody is asking a question in the chat. You're given data containing two classes of data. Okay, given data contains two classes of data with two features. Each class has four such data given. Now, how to estimate covariance matrix for LDA? Okay. Yeah, so it would be like you will have the within class covariance and the between class covariance. So uh, so so how can I write? Given data contains two classes of data, correct? Okay. So, and with two features. Each class has four such data points given. Okay. Yeah. So what you will do is you will take the mean of each class. Okay. The mean of each class you will take class 1 and mean of class 2 you will take. And so let's say the mean of class 1 is M1. The mean of class 2 is M2, right? So now, and what else do you have? Each class has four such. Okay, yeah, yeah. So now what you will do is you will take the within class covariance. So what you will do is for x1 minus m1, you will take this. You will do x1 minus m1 transpose. Okay, and this will be a 2 cross 2 matrix, because your data points are all two-dimensional. So this will be a 2 cross 2 matrix. And again, similarly, so if x1, x2, x3, x4, these are uh, your particular class 1, let's say. And similarly, y1, y2, y3, y4 are your class 2. So you will now take x2 minus m1, x2 minus m1 transpose. Again, this will be a 2 cross 2 matrix. And likewise, you will go up to x4 minus m1 and x4 minus m1 transpose. This will again be a 2 cross 2 matrix, and sum them all up. That will be the within class covariance matrix of SB of class 1, which means SB1, let's say. Okay. Similarly, you can calculate SB2 using Y1, Y2, Y3, Y4, and M2. So M2 and M1 is nothing but the sum of is the mean of all these points. So now you will be able to calculate SB2 as well. Okay. And the within class, and so this is all about the, sorry, this will be HW1, sorry, very sorry, this will be HW1 and HW2. This is the within class variance. Okay. And similarly, you can find out SB1, which is the mean of, so you will find out M2 minus M1 whole square, or M2 minus M1 into M2 minus M1 transpose. So you do that, and this will be your between class covariance matrix, and then you go ahead and do LDS as has been shown in the lecture. I hope this was okay. Yeah. Okay. So if there are no more questions, maybe I'll close the call, and because there are the four people in the call and nobody is asking any more questions. Okay, so thank you, everybody. We'll meet again next Saturday at 7 o'clock, at 7 p.m. Thank you.